Okay, so the second part of 10.3, this would be 10.3 part 2, is Dalton's law of partial pressures. Pretty straightforward law to calculate. What Dalton's law of partial pressures is saying is that the total pressure inside of a container is holding a gas. That total pressure is made up of the individual pressures of each of the gases in that mixture of gases. So if we could take out all the individual gases, measure their pressures, the total of those is going to be what the total pressure is. So notice this example from your book. It says if you take a certain amount of oxygen, so you have a 1 liter container, notice, at 0 degrees. This is also a 1 liter container at 0 degrees. So we have the same volume. This is also a 1 liter container at 0 degrees. So we have the same volume, the same temperature. That's important. So if those are constant, and we take a sample of oxygen gas that has a pressure of 0.12, a sample of nitrogen gas that has a pressure of 0.12, we mix those together. So we take this sample, and we take this sample, and we put them together. Well, the total pressure, notice, is just the total of the pressures of the individual gases. So P total equals P1 plus P2. And now this could work for multiple gases. Here's another example. Gas A has a pressure of 10. I'm not sure what units we're talking about here. It doesn't include them. Gas B has a pressure of 5. So notice they're both in, say, a 1 liter container, 1 liter container. Assume the temperature on both is maybe 0 degrees Celsius, 0 degrees Celsius. So we always want to be in the same volume, having the same temperature. If we put those gases together, notice their total pressure now is going to be 15, which makes sense. If this has a pressure of 5, this has a pressure of 10, now we mix those in the same size of container, obviously the pressure is going to go up. There's more gas molecules in a smaller space. The important key to that is the amount the pressure goes up is dependent, again, like we said, is the pressure on the individual gases, P1 plus P2. Now, it is entirely possible that you have a gaseous mixture that has more than 2 gases. Well, the nice thing is that this is not dependent on only having 2 gases. You could have multiple. So notice this is P1 plus P2 plus, dot, dot, dot. So you could have P1 plus P2 plus P3. As many gases as we need. Notice that is what this is saying. This symbol, if you haven't seen it before, is a summation. So it's saying the sum of all of the pressures is P total. So we could write P1 plus 2, or we could just say the summation of all of the pressures. And notice they're saying Pi. Sometimes we'd see this as N, the number of different individual gases, pressures of individual gases there are. So don't worry, we're not going to be necessarily using summations. It just means that we're adding up all the pressures. Okay. Often, however, what we are going to find is that we do not have the pressure recordings on the individual gases, because you might not have the individual measurements before you put the gases together. But often what we have is we have the mole amounts. And the mole amounts, since there's a relation between moles and pressure, we will be able to find the partial pressures from those mole amounts. So, that obviously probably didn't make any sense, but let's take a look at what this is saying. So we probably can figure out that there is a proportional relationship between moles and pressure. So if you have a cylinder of gas, this is supposed to be a cylinder. Maybe I'll have to redraw it so it looks more like a cylinder. Maybe an Erlenmeyer flask. It's my Erlenmeyer flask. And I put gases into it, and I put another gas into it, and maybe a third gas into it. Well, the moles are going to be proportional to the pressure. So as I add more moles of gas, that pressure is going to go up. So it's a proportional relationship. Well, the other thing then that is true is that because we add up all the pressures to find the total pressure, we also add up all the moles to find the total moles. So P1, notice, plus P2, plus P3, so on, is equal to pressure total. Well, it's also true that moles of 1, plus moles of 2, plus moles of 3, and if we add those all up, we're going to get moles total. Well, what we can use that for then, and I'm going to erase this for just a moment, is what this will tell us is that that same fraction, and really I want to rewrite this, the pressure of, say, gas I, or let's change that to a 1. The pressure of gas 1 over the total pressure is going to be the same fraction as the moles of gas 1 over the total moles. So if we know the amounts of the individual gases, we'll be able to calculate the pressure fraction, which is the same as the mole fraction. So this is a unit meaning mole fraction. If we had X, this X is the mole fraction. So what we can do very often is we'll know the number of moles. So we'll take the number of moles divided by the total number of moles. That will be the mole fraction. The mole fraction of the total pressure will give us the pressure of that individual gas. Seems like a lot of different variables here, but really not that terrible. All, again, that is saying is that if we can add up all the individual pressures to get the pressure total, we can also add up all the individual moles to get the moles total, and then the pressure fraction will equal the mole fraction. A little bit of rearrangement will allow us to solve for the pressure in every individual gas based on its moles, the total moles, and the total pressure. So, where are we going to use this? Often, what we're going to use this for is when we're collecting gases over water. So often, you can have a chemical reaction occurring. So you have magnesium in here with hydrochloric acid. The magnesium being more reactive is replacing the hydrogen. We're getting magnesium chloride and we're getting hydrogen gas. So the hydrogen gas is coming out, bubbling down, going into the water. Now it's bubbling out because the gas has a lower density than the liquid. If we measure the temperature, so we can measure the temperature pretty easily. We can measure the volume of gas that is formed pretty easily because it will fill up the tube. We can measure the pressure because the pressure will be the atmospheric pressure pushing down, but we have to make a correction on that. So normally we'll have a pressure total pushing down. That's the atmospheric pressure that's pushing down on this liquid surface, keeping the water up the tube. However, inside there is the gas we've collected, in this case perhaps hydrogen, and any water vapor. And where the water vapor comes from is the water vapor is the amount of the water that's in the gaseous phase at any time. So we can kind of think of it as when we bubble that gas through, there's some water vapor that is released along with that gas. And as our water gets warmer, there's going to be more water vapor. Now, we're not concerned about the volume of those water vapor droplets. I guess they're not droplets. It's a gas, so it's a vaporous. But we are concerned about the pressure. So often what we'll do is we'll subtract that partial pressure of water vapor from the total atmospheric pressure to find the true pressure of the gas that we've collected. Now notice most of our problems are going to be something like this. We have a 250 milliliter sample of oxygen. It's collected over water at 25 degrees. And here's the total pressure, 760 torr. It says, what is the pressure of the dry gas alone, the oxygen, if the vapor pressure of the water at 25 is 23.8? So we have our pressure total, and that is equal to our pressure of oxygen plus our pressure of the water vapor over the surface of the water. The total pressure, like it said, is 760. The pressure of the oxygen is what we want, and we know the partial pressure of the water vapor is the 23.8. So if we rearrange the equation, subtract 23.8 from this side and 23.8 from this side, we'll have our pressure of oxygen. So again, most of them not too terribly difficult to solve. Most of these we're just going to be subtracting. A few of them, like if we look further down, so those ones are kind of easy. I won't even do the calculation. This one's going to be a little bit more difficult though. And I'm not going to solve it completely, but we'll look at how to solve it. Notice this one gives us the moles of all the gas. It says we have 2 moles of hydrogen, 3 moles of ammonia, 4 moles of CO2, 5 moles of N2, and they have a total pressure of 800 torr. So we have a PT of 800 torr. It wants to know the partial pressure of each gas. Well, how do we know the partial pressure of each gas? Because we said already that the mole fraction is going to be equal to the pressure fraction. So if I know the mole fraction, N1, or N of whichever gas, times the total number of moles, and I multiply that by my PT, my 800 torr, that is going to give me the pressure of that individual gas. So if we solve for hydrogen first, the moles of hydrogen over the total moles times the total pressure is going to give us the pressure of hydrogen. So let's just do that one. So there's 2 moles of hydrogen. My total number of moles is 2, plus 3 is 5, 9, 14. So 2 over 14 times 800 will give me the pressure of my hydrogen. Thank you very much.